Good afternoon, everyone. Welcome to this week's HPL seminar. It's with great pleasure that today I can introduce one of the pillars of the HPL, Dr. Vinzenz von Tscharner. Vinzenz obtained his doctoral degree in biophysics from the University of Basel, Switzerland in 1977. Following his doctoral degree, he was a postdoctoral fellow at Oxford University in England and at Stanford University in California. Currently, Vinzenz is an adjunct associate professor here in the HPL, and he'll be celebrating 20 years with us next year in 2017. Vinzenz has a wide array of interests and has had a great impact on many different fields. You may actually consider him to be a Renaissance man. Here are a few of his career highlights. He spent his early career investigating neutrophils and inflammation. He has a first author Nature publication to show for this work. He later worked for a bank as the president. When Vinzenz began working in biomechanics in 1997, within 3 years, he published one of the most significant advances in EMG technology since electromyography was first discovered. I'm referring specifically to his technique using wavelets to extract information from EMG signals. Vinzenz also has the distinction of publishing 3 articles within a single volume of the Journal of Electromyography and Kinesiology. That wasn't good enough, though, because the very next year he published 5 articles in a single volume in the Journal of Electromyography and Kinesiology. So many different groups here in the HPL can attest to Vinzenz's mathematical prowess, and he's been a key driver of the technical and analytical progress on many of his collaborative projects. The impact of his research is very clearly demonstrated by the 4,000 plus citations that he's accumulated over 97 peer-reviewed published articles. Now, while Vinzenz has an office here in the HPL, he prefers his office at home, deep in the woods in Braid Creek. You can see a moose in his front yard. So his office in Braid Creek consists of his deck chair and 2 piles of books, one on the left and one on the right. So today we have a great opportunity to hear Vinzenz speak on his research program looking at EMG in the seminar entitled EMG Vadis. So take away, Vinzenz.
Hello, everybody. This little moose came to visit me and watched me while I was preparing this talk, looked for food, and was a bit puzzled of what I'm doing. So my main interest that I have is in the neuromuscular control. And so it's that whole circle, starting from the brain. Oh, leave the light on, please.
Sure.
Starting from the brain, going to the spinal cord, then we have the innervation zone on the muscle, we have the sodium-potassium fluxes, and in fact we have the activation of the muscle, and a lot, or the main part of my talk will be about this activation of the muscle. We then have the muscles that generate the movement, and the kinematic experiments that we know in this laboratory. And so here now the proprioceptors and the sensory system feeds back to the brain, and so this is working in a loop, and in fact we can access one part of the loop by measuring the EMGs. If you look, where is the border of knowledge? And so the border of knowledge is represented here with this white line, and on one side we have the known aspects, and on the other side we have the unknown aspects. And one of the tasks we have is to see where is our project. If the project is a pure engineering project, so we develop and improve our system in such a way that we can do the research. On the other hand, we have research projects in the unknown, and if these research projects are too far away, then in fact we will not reach them, or we are unable in our lifetime to reach them. If they are too close to this border, people will say they are boring, or not very relevant, or trivial. So it's always a balance between these two passes. Are you close to that border, and can you move that border? What is the path to innovation? The path to innovation starts, in fact, by criticizing. Criticize yourself, criticize the others, criticize the thoughts, and in fact go through all of this. Look at the publications with a very skeptical way, see what's wrong in there, see what you would do differently. And so this is really a mental activity that is important. And if we look at many of the studies, even studies done here, we have the phenomenon no results. And this no result is often a case because we have not looked at our own projects with sufficient critical mind. The next step is we have the wrong model or the wrong method, and even with the wrong model and the wrong method, we get correct results. So think about the ancient time when you thought that the world is a flat place, not circular, and in that case, you could navigate very well with a wrong model and with a wrong method. So we are not always as precise as we think we should be. One important thing in innovation is don't accept dogmas. If they tell you all the time an EMG is measured with potentials, it needs to overcome that dogma to say we measure now the currents. So dogmas are in fact something that are preventing innovation, and you have to overcome them. So you have to revisit all the beliefs that we have. In fact, challenge these beliefs, otherwise you won't make any progress. One important thing that you have to decide on a project is whether it's relevant. And relevance can be either for you or it can be for others. So if a project is not relevant, I would suggest don't touch it. I can tell this from my own experience. I went for my PhD and I got a very challenging topic, measuring currents in ion channels. I was fascinated. The first day I arrived, they changed my topic to a completely different topic, cooperative binding. And I thought, well, now I have a position, I have a job, I have a salary, so let's do that new topic. I finished, and when the professor next door came to congratulate for my PhD, he said, you made only one mistake. Your mistake was to accept the topic. And it was never cited. So we have a very interesting thing that comes out from my dowsing experience and from the work that I have done on dowsing. In fact, you have to accumulate knowledge, and this accumulated knowledge sinks in. But then you have to work with your intuition. So there are different ways to work with intuition, but it's always the balance between consciousness and subconscious. The intuition comes from the subconscious. Consciously, you acquire knowledge, you think about your stuff, but you have to let it go, otherwise you have no intuition. So you have to play with these ideas. And you can in fact train that circle, because your subconscious is far bigger than your conscious. So your subconscious work is far more important than your conscious work. So keep that in mind when you want to do any innovation. And finally, you have to debate these things with your colleagues, with your friends, and often these debates become hated, but you have to take this and you have to do this debate, otherwise you have no innovation. And then the least thing and the last thing is, with all these ideas, you've got to do it. So let's look for today at the circle of three things that I want to talk about. One is, of course, the muscles, placement of electrodes, and so on. then our amplification system, and then most importantly about the signal processing that we have here. If we look first at the electrode placement, and now look at this in that critical way that I meant before, what you can see here is in fact electrodes of that 1 centimeter diameter that is usually used in this laboratory. And if you look at an ultrasound image of a muscle, and you look at its size, then you see here a gastrocnemius muscle, and you see the pennation of the muscle fibers. I have now just taken that measure, made the little yellow stripes here, 1 centimeter each, and as you can see, the innervation zone is somewhere in the middle of this thing. So somewhere here is the innervation zone, and so you are just hitting exactly what you should not do with an EMG. Never put the electrodes on both sides of an innervation zone. On the other hand, how would you get the electrodes in the cross-section of a gastrocnemius? You would have to come from the side and maybe even cut the muscle to get there. So normally our electrodes are on the top of the skin and not on the side of the muscle. And finally, if you look at these electrodes, they are huge compared to these fibers. These fibers are about 6 centimeters long, and your inter-electrode distance is 2 centimeters. That's like using a sledgehammer on a muscle. Even worse, if you continue, what you see is now the muscle contracts, the pennation angle changes, and so suddenly your electrodes are not anymore aligned with your muscle fibers. So in fact, in a dynamic movement, during the movement, your muscle changes its orientation under the electrodes. So one way that one can bypass these things is to use a single electrode. It might still be a big electrode, but at least you can place it on the surface of the skin, or you can place it somewhere that you are on one side of the innervation zone. So it's much more flexible to work with one electrode than with a bipolar system. And so we started working with these monopolar electrodes. So let's look at an experiment that we did here with monopolar measurements. So we made the monopolar measurements on 4 electrodes that were located on the gastrocnemius muscle. And then we looked at these electrodes and we made a different signal, like a bipolar signal, by just subtracting one electrode's signal from the other. And then we plot this in the XY plot here, and what we can see, the 2 signals are not correlated. So in other words, a bipolar measurement measured here and measured here are not correlated. However, if we look at the monopolar measurement of one electrode here and one electrode here, we suddenly see that these are highly correlated. So what does that mean? That means, in fact, that we lose by the common mode rejection. So each amplifier has a common mode rejection, which means when 2 signals arrive simultaneously on both poles of the amplifier, they are cancelled out. So in other words, when 2 signals come in synchrony, then they are cancelled out. So this experiment showed that in fact we cancel out exactly those motor unit action potentials that are synchronized in the same muscle if we measure with bipolar electrodes. So part of our signal is gone. Now, that's absolutely unimportant, wrong model, wrong approach, but good results. It tells you exactly when the muscle is active, when the muscle is inactive. So a lot of the past work that is done with that system told us the onset and the end of muscular events absolutely correctly, but they leave out the synchronized motor units. So what have one done in the past? In the past, here you see the sum, and then you see the electrodes. It's a 2 centimeter inter-electrode distance on the hand muscle. Where would the innervation zone be? The innervation zone is somewhere in the middle. And so again, we are making a measurement. We get the perfect signal, and this publication showed the expected result. That was force enhancement, force reduction. We saw absolute perfect result with huge electrodes on a tiny, small muscle. So in fact, Marina Barandon was here, and we said we have to change things. So we changed things by, in fact, making our own electrodes, having a silver rod, and we cut these pieces of silver rod and made electrodes that had only 6 millimeter inter-electrode distance and were only 2 millimeters in size. So they were appropriate for this muscle. We measured then in a bipolar way, always 2 electrodes, 2 adjacent electrodes. And if you do it that way, then you can see that you get an EMG signal. We call it the source because it's closer to the innervation zone. And then you get the response signal, and you can see that the response signal is absolutely identical or very, very similar to the source signal. In fact, a little bit lower in amplitude because it's further away, and because the conduction velocity of all the fibers is not the same, so you have a damping phenomenon as you go further from the innervation zone. If you would do that on these electrodes here, then you would see the signal flipped, and you know exactly where the innervation zone is. So having smaller electrodes, you can in fact place them correctly. If you look at other ways of measuring EMGs, we used an array around the leg, a little bit above the ankle joint. And now if you do that kind of electrode positioning, then you can in fact see here the circumference on the x-axis of the leg, and then you have the intensity, and so now you have these 4 muscles, and you can see where, so that is heel strike for walking, and so you can see exactly where the muscles work, and when is, for instance, the tibialis shut off, while the soleus lateralis is switched on. And so you can see that we have internal differences, regional differences in the muscle. And so we have developed this technology to follow, in fact, to watch the interplay of the muscles. Quo vadis, where are we going with that? I think it's very important to use the ultrasound to place your electrodes. As you have seen, the muscle is not homogeneous, and so you start with a Senium protocol, you use the ultrasound, and then you know exactly where you are, you know your size, and then you can in fact decide which is the appropriate technique. Do you want to measure monopolar? Do you want to measure bipolar? Do you want to measure potentials? Do you want to measure currents? You have to decide these things, and we will be much more in the future attentive to these kind of decisions. You have to consider what you lose. We have just seen that single experiment where you lost, in fact, all the synchronized motor unit action potentials. So that doesn't mean that you can't measure, but you measure only part of your signal. And so in the future, we will have to build our own electrode arrays and specifically make electrode arrays that fit our muscles. Now let's progress to measuring to the inter-electrode distance. The inter-electrode distance is a very important aspect in EMG measurements. If we look at the work from the Italian group, and lots of work has been done by these Italian groups around Melletti. And so what you see here are 16 electrodes, and they were spaced with 5 millimeters. So you have 15 times a bipolar measurement. And so you can now look at one of these motor unit action potentials. So one of these potentials is in fact the differential of a motor unit action potential. On the bottom you see the scale. This was 10 milliseconds. Now you can draw a line from the peaks of these motor unit action potentials. And so because this axis is distance, and I moved that line here to the corner, you see we have 6 intervals on 10 milliseconds. And so this is 3 meters per second or 3 millimeters per millisecond. So in other words, that way you can measure the conduction velocity. Now, critically seen, we put electrodes of that size on this motor unit action potential. And you can see with 1 centimeter electrodes, you don't measure the differential of a motor unit action potential. You measure a signal, but it's not really relevant. So that causes troubles. Another nice thing to realize is that this signal, this single motor unit, is in fact 3 centimeters long. So in fact the motor unit is not a little spike somewhere on your muscle, but has a real geometrical size. So many people don't realize this. Now 3 centimeters on some thumb is practically the whole muscle. So your motor unit action potential is not a little spike that travels, but it's a whole activation over the whole muscle. These are kind of reflections about the system. So, Quo Vadis with electrode distance. I think we should gradually move towards more sensitive amplifiers and reduce our inter-electrode distance to 5 millimeters. And we should then work with arrays and not with single electrodes in the future, so that we capture, in fact, the anisotropy of the muscle as well. We further should see that in a monopolar measurement, you measure a power spectrum. And the power spectrum of the bipolar measurement should be the differential of the monopolar power spectrum. So we should, in fact, compare these spectra to know that we have a real differential, that our signals, monopolar or bipolar, are equivalent. When we now approach the 2 electrodes and make them closer and closer, you have a skin resistance. And so with the skin resistance, ultimately there comes a point where you have a short circuit between your electrodes. So you cannot make this distance infinitively small without having this result of short circuit. However, when we measure currents, we keep the electrode at ground potential. And so with a current measurement, we will not have any short circuit between electrodes. And for that reason, our next thing will be to build a bipolar current amplifier and to test this bipolar current amplifier versus the classical way that you measured. So now let's look at the amplifier. We had a nice presentation a short while ago in this seminar. I just want to repeat the main features of it. In fact, Daniel has built a lovely little amplifier, a monopolar current amplifier. And what you see here is the characteristics of the amplification of my first prototype. And in his master thesis, he improved it to the size of the green one. Now we have a flat domain, meaning constant amplitude across the relevant frequencies of our signal. We have a very sharp drop in the low frequency end that avoids movement artifacts, and we have a strong drop that avoids aliasing of our signals. So in fact, not only the bought equipment or the standard equipment is not perfect, but we have possibilities to improve our amplifiers so that we get better results. So Quo Vadis amplifiers, the next step I would like to see is that we have a filter unit on the end that Daniel has developed. And then I would like to have different heads for the amplifier so that we can, with the same system, once measure a monopolar current, once a bipolar current, once a bipolar voltage, and so on. And so we can see whether our system is really behaving as it should. So not just strictly put something on and hope you are correct, but put it on and check it. I would like to go now to the signal processing, which is the more interesting part of the work, but it needed a good signal before we can do any signal processing. So, of course, we can first look at amplitudes, but mainly I'm interested in spectral aspects of it, and the spectral aspects include coherence analysis. Spectral analysis, in fact, you lose your time information. That's why you have to go to wavelet transform. We have to go to the wavelet coherence. Today, I won't speak a lot about pattern recognition, but you can, in fact, then use pattern recognition to discriminate between movements, between certain activities. And finally, we start to realize that the EMG is not random. These signals are all but random. And so we need measures that can access the variability. And one of these measures, and I won't talk a lot about it, is the entropy, which is a measure for order. As you know, entropy is a measure of order. And so you can measure an order in a signal, and you can see whether an EMG signal is random or non-random. So let's look at the signal processing. And here I have from Morris a nice measurement from walking, where you see two signals that were recorded from the vastus lateralis and vastus medialis. And now we do a wavelet transform. So the wavelet transform leaves the x-axis constant, same axis as here. On the vertical axis, we now have frequency bands, and these frequency bands are resolved by the different wavelets. And each wavelet, in fact, detects the power, and the square root of the power is the intensity, and the intensity is now color-coded, and the color-coded intensity is shown as a pattern. So this is now a different way of looking at the amplitude of an EMG signal. Now, a couple of months ago, we still were practically thinking that these patterns, they look pretty random. So what is the information in there? Do we have any? But if you look at this, it's really striking that on two muscles, without having any crosstalk, we made sure that we don't have crosstalk, you see patterns that are almost identical or extremely similar. So our central nervous system is able to generate a muscle activity, an EMG signal, that here would look almost random, but when you make the wavelet transform, you start to see that this thing is not random. However, when you go to the next step, you see it's still similar, but the similarity is far less than between the two muscles from one step to the next step. So in other words, the EMG changes from one step to the next. Now when we form the average on all these EMGs from all these different steps, what we obtain is here an average signal. And so the average signal has a band. Now the interpretation of an average signal is completely different than the interpretation of an EMG from a single step. When you make the average, this signal represents the probability that the muscle will be active at a certain point. But you will never have that mean as an EMG of an actual step. So you need a new interpretation, a probabilistic interpretation, when you want to look at means of a wavelet transformed signal. What you can see here is that even during that activity on the mean, you have the two bands and you have events within that overall event. So an event is modulated. And so these modulations were gradually striking us, and we thought they are important and relevant. They are in fact responsible of how, in fact, our muscles control the movement. Let's go back to our measurement on the Abductor Pollicis Brevis. And what we see here is now the spectrum, the power spectrum of the source and response of these electrodes that I have shown before. And so now you can see the spectrum here. And initially you would say these oscillations here, they are just random noise oscillations. And they were interpreted as this for many, many years. However, if you think that the source and the response are two separate measurements, you suddenly have to think, how is it possible that the source and the response have exactly the same modulation in the spectrum? So in other words, these oscillations are not noise. They are really coming from our signals. So we start scratching our head and said, where is that coming from and what does that mean? And now, in fact, Mike made, he is not here now, but he made with me this model calculation where we said these motor units have to cluster. So motor units are not, as it's said in the textbook, randomly distributed, and they don't come randomly, they come in real oriented ways, and they are clustering. And so if now you make a random clustering by taking one of the motor units, as I have shown from that Italian work, we just copied that motor unit action potential, and then we convolved this with a pulse train, and what we obtain as a power spectrum is a relatively smooth, nearly normally distributed power spectrum. If we now take the same number of motor units, but we cluster them, and we cluster them randomly, then suddenly we obtain a completely different power spectrum. Now what you see here is that completely different power spectrum has practically a shape that is really similar to what we observe in the real power spectrum of this Abductor Pollicis Brevis, which is the first indication that in fact this is not a random distribution of motor units. Also, the activity was more or less isometric at the time. So now we have this model, and Mike will talk in another talk more detail about this model. But what we have now here is the walking spectrum. And the walking spectrum also shows these interesting fine structures, and the way we make a power spectrum, we are able to have an error measurement, and so we can see that these peaks are not noise, but these peaks are significant. So, where do we see clustering in real experiments? So, we had an experiment with Christian Maurer where we tested runners, and we tested runners at different speeds. And if you run at a low speed, low speed, in fact, you don't see much structure in your EMG. So that's practically now the envelope, or the root mean square of an EMG, or we do it with the wavelet transform. So it's the intensity, or here it's the power. And as you go to higher velocities, you see that these rhythms become more and more pronounced. So if you have a high demanding task, then in fact your EMG is pulsed. And this pulse is called the Piper rhythm and was first detected roughly 1907. So it's a very old finding. People forgot about it until the end of last century. And with the wavelet analysis now, we are really able to detect these rhythms very, very nicely. Now, imagine you have such a rhythm. How would you explain such a rhythm from the point of view of your motor unit action potentials? If they are randomly spread, you would not get a peak. So in other words, they have to accumulate exactly at these positions where you have the maximum of the Piper rhythm. So what can we say with the clustering? So clustering lowers the frequency of the power spectrum. We have seen that shift in that one slide. It adds fine structure to the power spectrum. So suddenly, the information in the power spectrum has now an additional aspect of it. We can see the effect of clustering in a power spectrum. Now, one of the standard routine measurements is fatigue. And fatigue is measured in an EMG by the lowering of the mean frequency. Now, 90% or 99% of all experiments on fatigue that has developed that technique of lowering the mean frequency were done isometrically. And whenever people started doing this in a dynamic exercise, once they saw an increase, once they saw a decrease, but the literature is really inconsistent. And now with this clustering, you have to see that we have a competing aspect. So if the clustering changes during a dynamic movement, then in fact you are changing your spectrum. And this is now competing against the fatigue effect. And that's why in a dynamic measurement, in fact, the fatigue just as lowering of the frequency is not correct. So a big task for the future will now be to separate the peripheral fatigue and the central fatigue. So these clusters are in fact the central phenomenon controlled by the brain and the spine. And so if these change with fatigue, then we have two effects of fatigue, a peripheral and a central. And we need to separate them in the future. So let's continue and look a little bit more what that means in the sense of the preferred movement. Preferred movement is a topic that Benno, Nick likes very much to talk about. Preferred movement means you walk, you see a friend walking in front of you, you immediately recognize the movement pattern of your friend. Whether he is barefoot, with shoes, or with boots, you recognize that person. And then was a striking finding over years that in fact the kinematics did not change. So you could put on shoes, you could put on this experiment, that experiment, but usually what you find, minute changes in the kinematics of the movement. Now, what does that mean for the EMG? That means the EMG, in fact, has a task to adapt the movement to keep the preferred movement going. And so the variability is not in the movement, but the variability is in the EMG. And so if we look back at Morris' walking experiment, we can now clearly see that the next step is similar but not identical. But what we have learned from here is that these clouds, these patterns, are not random patterns, but these patterns have a structure. And so encoded in this structure is in fact the variability, the information that allows you to have a preferred movement. So in fact, if we look at Quo Vadis with the preferred movement, the EMG varies to keep that movement constant. And in the next future, we have to learn to deal with mathematics that allow us to handle the variability and to handle the variability of the intensity patterns. So this is future tasks that students should address. And in fact, what we have started, we have the first publication with Hendrik, where we in fact saw this variability and resolved it by using fuzzy entropy. And we have now with Maurice certain data that show that we can even see fuzzy entropy and measure fuzzy entropy in the raw EMG signals. So this is a completely new pathway that will be addressed in the near future to see how is in fact the central neural system changing between random and absolute controlled system of the EMG or of the muscles. So now we have seen that we have this clustering and we have synergistic muscle activities. And so let's look a little bit closer at the vastus medialis and vastus lateralis muscle, and let's use that mathematical method, the coherence analysis. So coherence analysis is relatively simple. It's simply the correlation between two signals. But first you do a Fourier transform, you isolate the single frequency band, and then you look in that single frequency band whether your signal is correlated, yes or no. And you correct, in fact, for the phase, so that it becomes phase independent. So it's a phase independent correlation at the specific frequency. And so coherence, like a power spectrum, will have one coherence for each frequency band in a power spectrum. So much to the definition. We made some experiments where we have a dynamic squat on the right-hand side, and we had an isometric position that corresponds to the squat, where the person was leaning against the wall. And then we measured, in fact, the two vasti muscle, and you can see that if these two muscles are not matched, we will have a lateral force on the knee. So in other words, if these two muscles work in synchrony, the knee is straight. If they would work asynchronous, the knee would shift. We measured these using our little current amplifier, at that time still the prototype. And what we can see here now is interesting. So we split the squatting movement in the eccentric and the concentric part of the movement. And now what you see here is that in red you have the concentric part, and the concentric part starts here with a peak, and then a second peak, and then a modulation. And if you go to the eccentric movement, in fact your spectrum changes to the green one, so that peak moves. And this is the difference in black between the concentric and the eccentric power spectrum. Just to remind you, lots and lots of people have looked at concentric, eccentric measurement and saw no difference. So this is relatively new, that you can, in fact, see differences in the power spectrum. If we look again whether these oscillations are random, we have a completely separate measurement on the other muscle. So the vastus medialis muscle shows a very similar pattern with the same movement and with the same difference between the concentric and the eccentric power spectrum. Finally, we look at the coherence, and so we see here that the coherence also has oscillations. It has a maximum around the 40 Hertz, so it has a maximum around the place where these spectra are, and this coherence would have a maximum of 1, which is up here. So in other words, it tells us that these motor units are highly synchronized. They're not just a little bit synchronized. Otherwise, we would never get the coherence close that high. And you can also see that the coherence happens in certain locations and in bands. So we have a high frequency band with a significant coherence, not as high, and we have the low frequency band. And so we have now to think what is creating the high frequencies in a power spectrum, what is creating the low frequencies in the power spectrum. So the low frequencies are mainly that wave that I have shown you before in the Italian group. So this is the wavelet this is the wave, the motor unit action potential that we used in our model. But in fact, if you look carefully, you will see that each motor unit has a fine structure. And the fine structure reflects the end plate structure, the end plate arrangement. And these arrive in the higher frequency domain. Now, we look at the result of these squats. Now the dynamic squats again. And what we see, the comparison is that in a dynamic squat, we have a very high coherence again, 0.7 at about 40 Hertz. And then we compare that with the EMG leaning against the wall being in that squatted position. And now you see that, in fact, your coherence dropped significantly from that high value that you have during the dynamic exercise. Now, we needed to have a measure whether these coherences were significant or not. So we shifted the signal one towards the other. And at that point, if you shift sufficiently, you have no more correlation between one and the other signal. And so if we look at the shifted signal, then we obtain what is the baseline for the coherence. So we see even in isometric, we are above baseline, but we are much lower than in the dynamic. And so what this means is that synchronization and coherence, in fact, is task dependent. So it's not something that is always there, but it's something that is controlled by our central nervous system. So let's go back to the wavelet transform and see what we can do with a signal of walking. I have a little bit more time. Do I have time until? Okay. If we go to a signal like walking, in fact, this coherence analysis fails. And it fails because our signal is only 250 milliseconds long, and one of these blips is only about 30 to 50 milliseconds long. So in fact, we have not enough data to make a Fourier transform and to really go. And so we have to go back to the wavelet transform. And a few years ago, I published an article about how to do wavelet coherence analysis. So for the first time now, we have a wavelet coherence analysis, and we don't know all the interpretation yet. We only know that when we shift the signal, this coherence disappears. What it tells us is that while we are walking, in fact, there are areas, the dark blue areas, where the two muscles are mostly working independently, stabilizing the movement. Whereas there are some areas and some persons, some subjects, who really show significant coherence while they are walking. So we have a kind of pendulum during the stabilization of a walking movement that uses synchronization whenever it's needed, but not all the time. And that makes the analysis now more and more difficult. So future work will be to analyze these patterns that we have seen and then see how these patterns can be incorporated. So that means working in a vector space. That means finding surfaces in a vector space. That means to find intersection of the areas in vector space. There's quite a complex domain of topology that we have to address in the future. So the wavelet patterns show distinct bursts of EMG activity, and I hope I have persuaded you they are non-random. So we can take them for granted. So an aspect that we haven't touched yet is if you have these bursts, and they have any significance in stabilizing a movement, they must create a force. And one of the big challenges for the future will be to find how can we measure forces with such an accuracy that we can see the fluctuation caused by the dynamic changes of the EMG signal. And then I was thinking about these clustering and about this synchronization and the continuous change of the synchronization. And I read an article that took an EMG from the back of the ear and used, in fact, the power spectrum to control a prosthetic system. I don't know what it was, an arm or... No, it was just a thing on the screen that they could move then. So, in fact, somehow it seems that we can mentally influence this thing. So I asked Daniel to say, can you measure this? Can we see whether we can mentally influence this synchronization? And if so, would that be a training method? Could we use that in sports activity for athletes to improve their stability? Or, as Maurice is doing a study in osteoarthritis, could we use this to help during a rehabilitation process? So I think especially in the rehabilitation process, that would be very interesting. And one of the hypotheses that Maurice is using for his PhD thesis is that this asynchrony that we have, in fact, now causes micro-shear forces in the joint. And so these micro-shear forces would be an alternative than having high pressure on a cartilage. And that comes back to the question, can we measure, in fact, the forces of these micro-shear forces? Are they accessible? Up to now, with all the techniques that we have used in Walter's group, we were not able to see these forces. So there is a big challenge for that. So now we look at the biofeedback, and as you can see here, the subject was asked to move a line here that in fact represents the coherence between the vastus medialis and vastus lateralis. And so if now the person can concentrate and mentally shift this line upwards, then we have the proof that in fact you can mentally change your synergy between muscles. And so if we look at the result of this, what we can see is for 10 subjects in this experiment, the green one is the control and the coherence of the control, and the orange one is the biofeedback, how much they could in fact push up this coherence. So that tells us that we can mentally in fact control the coherence. Now that opens a whole lot of new possibilities for studies for the future. When is that important? How is that useful? Would that mean that the nerves would grow and change and use the plasticity of the central system to improve whatever, stability or rehabilitation? So this biofeedback machine with a real-time measurement of coherence, previously it took us a very long time to calculate coherence, now we can do it real time, so that opens this for physiotherapists or for other groups. So if we look at that, we can change that synchronization, means we can change the clustering. So I don't think that what this group has measured with the ear was a change in fiber type that changed the power spectrum. But I think it's much, much easier to change the synchronization of motor units. But the synchronization of motor units causes the clustering, and therefore, in fact, it changes the shape. So in other words, we can mentally change the shape of a power spectrum. And that means we can use the power spectrum as a driving unit for a prosthetic control. So the future will show whether, based on that idea, we can develop further elements. So we have talked about this clustering, synchronization of motor units, and that whole system must be controlled centrally. So we have to prove, to show, in fact, that this thing is centrally controlled. And so Hendrik did his PhD on that idea that there must be a correlation between the signal in the brain and the signal in the muscle. And from this running study, where we have seen the Piper rhythm, these rhythms, and we have seen that these rhythms increase with the kind of challenge that we had. Running faster gave a faster and more pronounced rhythm. We said we cannot, in fact, measure this isometrically, because isometrically, the brain doesn't care too much. It gives a command and the muscle is active, and we don't expect too much brain-muscle interaction. However, if we do that in a dynamic situation, on a cycle ergometer, going to 150 or 300 watts, then, in fact, we should see more and more of the coherence between the brain and the muscle. And so, in fact, the first measurements that suggested that there is a brain-muscle interaction was Brown and Salenius and these people, and they have shown that, in fact, between the motor-cortex, they used the forearm extensors and used the motor-cortex in the cerebellum as one source, one signal, and the other signal was the EMG signal from the forearm, and they could show a relatively small but distinctly above the noise level, a coherence that occurred. So that was the first time that you could see there is a brain-muscle interaction. So that gave us, in fact, the hope that if we plan to make such an experiment, we could be successful. And as you increase now your contraction, you see that you reach this peak here. So in fact, you shift that to multiple peaks. So multiple frequencies now become relevant. And if you think back to my talk now, that is amazingly on the 40 hertz. So that is more or less what the clustering is doing. That is exactly on the 40 hertz that we observe in the muscle on the thumb. It's exactly what we observe in the walking. So this 40 hertz or around 40 hertz signals are in fact the signal that come from this clustering and from this brain-muscle interaction. And so, in fact, Hendrik did this work, and what you see here is first the rectified EMG. That is the top position of the pedal of the crankshaft. And then here now you have the frequency bands, and here you have the pedal revolution, and in color code you have in fact the coherence. So the coherence between the EEG was possible, and we can clearly detect it on this cycle ergometer. But compared to the 0.1 that Brown observed, we have now suddenly correlations in the order of up to maximum 0.8. So the brain signal highly correlates, in fact, with the muscle activity. And what we see here is that when you cycle for a long time and you get fatigued, you in fact lose that ability to really get the brain to make this synchronization, and your coherence now decays. So in the fatigued state, you have less coherence than you have in the fresh state, having the same power output. So with that in mind, and you have seen here, I have Andrea Protzner. We will meet next week. Daniel will most likely work on improving the amplifiers we use for that experiment. And there will be a collaboration between the EEG lab over there and our group to continue that part of the work. With this, Mahmoud turned around, looked at me, shook the head. That's not my cup of tea. Moose said, I don't understand this. And now both of us will return to the forest. With that, I thank you very much.
So what do you think about the recruitment pattern of the motor units? So do you think that they are recruited slow to fast, or small to big, and then at some point they would cluster together and become synchronous?
I think it's very much a matter of how the experiments were built up. These recruitment patterns have been made on experiments where you gradually increased isometric force, one after the other, and then you could see how practically additional motor units were added. And so we have all this work of recognizing the different motor unit action potentials and have a theory of recruitment. I think this is very theoretical and very, let's say, lab-oriented. In practice, I think that's not what happens. In a practical term, we have to discriminate whether we need motor units that are used for constant force, so hold. And we need other motor units that are aimed at a fast movement. And I think the body will recruit the motor units for the purpose. And this has not been investigated in the literature. Simply it was not possible. And so I think that the body really selects this. Also, when you look at the motor unit in these aspects, they come periodically. And if you look at the interval between them, the interval is in the order of 30, 40 milliseconds or longer. You have some that are shorter, but the majority is bigger than 30 milliseconds. So if you look at the Piperism, one motor unit can only fire once. So in other words, in a movement, we don't have that repetitive motor unit activity. What the brain and the spine has to do is take those motor units that are important for that task and focus them in a very short 30 to 50 millisecond pulse. And then they are active. And use the right motor units. Use the fast twitch or the slow twitch or whatever is important for the kind of movement.
A question around the controversy of a random muscle contraction being necessary, and random recruitment being necessary in order to cause a smooth contraction, which is kind of in contrast to the idea of an order in a muscle contraction to optimize force generation. I was just wondering what you take on that argument.
Well, there is a lot of unknowns in that. And one is, in fact, the delay, the electromechanical delay. So the question is whether the EMG signal is precise, and because of the delay, in fact, the force becomes smeared out. I personally don't believe that. I think it's simply because we don't have the right tools to measure the forces to that accuracy. If you look at a balance test and you look at the muscles of the leg during a balance test, you will see that, in fact, the control mechanism is also in bursts. So the movement is controlled by bursts. And one of the bursts makes a force that accelerates the body, and there will be no more burst or no more muscle activity as long as the body constantly moves in that direction, until your sensory system tells you you are going in the wrong direction. And then you will have a small pulse of force that brings it back. And so that's what is in fact behind the entropy measurement, is the longer you make no change, in fact, the more controlled is the movement, and so the lower is your entropy. If you have a bad stability and you constantly have to control, then you see your entropy increase. So with the entropy, we have an access to these kind of questions.
Good question from the web.
Yeah, this is being webcast, so somebody that's attending the webcast has asked a question, and their question from Alice is, how do we mitigate input noise using monopolar electrodes?
Well, with monopolar electrodes, we have, in fact, more movement artifacts. That's why we haven't used it for the moment, and I don't know where I should look to speak with that person. In the camera. So, in fact, that is why we built a new amplifier with a much higher drop in the low frequency, so that, in fact, we remove more of the movement artifacts. That's, in fact, where we are now doing our current research. We are not yet there that we can use it for running. Whenever you hit the ground, you have an impact, you have a movement artifact. So, in fact, we have, for the moment, we can measure small movements like squats, like shaking a leg, sitting on a table, and so forth. So a lot is possible, but not, in fact, sports activity yet. But what I hope to do is that gradually, with the bipolar amplifier on current, we will get access to these kind of things.
They responded, thank you.
I have a question. So it sets the motor units fire in order to maintain the preferred movement pattern. What happens if someone lacks proprioception or they're doing a completely unfamiliar task?
I think that's exactly what you see. For instance, there were studies done here in the lab by Wakeling. You walk on a solid floor and then you walk on a carpet. It needs one step and your human body has adapted. So the adaptation is relatively fast, but it's a feed forward. And if you see an object, you can bypass it. So your brain, in fact, is able to adapt according to what you see. But if you're in the dark or you are not attentive, and even if you have just that much of a height difference, you stumble. So, in fact, you need a certain recovery time until the body finds the new pattern that is used for that circumstances.
Do you have any ideas why 40 hertz seems to be that special number?
No, I have absolutely no idea. And it's most surely not 40 hertz precise, but it's the area 50 to 30. Let's put it that way. But it seems simply to be inherent to the physiological properties of the body of having a conduction velocity between 3 and 4 meters. Why don't we have 6 or 7 meters per second? I think it's just similar there. Also, we have certain narrow ranges, and these narrow ranges lead that also the frequency is most likely in that kind of range, and as we can see, it corresponds to the frequencies that we measure in the EEG, and so it seems that is kind of a frequency that patterns are using in the human body.
If your feedback experiments where the person was able to train themselves to increase their coherence, did that persist for an extended period of time after? And did you test if without the visual feedback of their coherence moving up and down?
These are all questions that are now open for future research. We just looked, is the machine feasible? And we looked at what is fatigue doing. So we can see that this coherence decays with fatigue. So we can have now a measure for central fatigue. But we haven't really gone any further yet, and I hope I find new students who would work on this. And do something with what we have developed previously.
When you're talking about, you made a statement that you control the EMG so that the movement is always the same, right?
Yeah.
That you have, so you know, for me, that makes me think that if somebody is walking, you set up a very rigidly forced pattern of EMG such that the kinematics don't change and that their gait is always identical.
No, just the opposite. You set a very rigid pattern of walking, and you adapt the EMG to maintain that pattern. So not the EMG is rigid, the walking pattern is rigid.
So how does the body say, oh, if I'm looking at, say, three muscles that are synergists, how does it determine a pattern where the three contribute to the gait of, say, the person? Because there is variation there. So I mean, some of Walter's early work looked at cats walking on a treadmill, right? Very even gait. But if you look at the EMG and the forces in the three synergists for the ankle, the flexors, it's actually all over the map. They change all the time.
Yeah.
But there isn't really time for the brain to say, oh, I've turned up the soleus too much, I better back away on the plantaris, right? There isn't time for that to happen. So how does that work?
You're not very, you don't have a big belief in our brain. I would say that's the amazing thing about our brain. And the amazing thing is that we control all these movements, whether it's walking, but especially if it's tennis, ping pong, the faster you go. Imagine how is the brain able to control all these movements with 3 meters per second conduction velocity. That's incredibly slow. Imagine that you have a meter or 2, 1.5 or whatever between your brain and your knee or your ankle. Then, in fact, you must have a complete feed-forward control from the brain with a high degree of tolerance. And I think in this Piperism, what you see, that is more or less 30 milliseconds long. And that is the cycling frequency of that cycle between brain, muscle, and feedback. And so at the rhythm of about 30 to 40 hertz, in fact, you make your corrections. And in the meantime, you go with a given pattern.
I think I would argue that perhaps saying that the movement is constant is probably, it's probably not, but it doesn't really matter how you produce the forces. As long as you don't produce a net force that's much bigger or much less, it doesn't matter how it's doing. But maybe we shouldn't be looking at whether the movement is highly controlled when we look at it from a camera. Maybe that's simply not important.
I fully agree, and that is exactly what we observe. If you have a large dimensionality and you have a non-challenging movement, so I take a plateau with lots of glasses, all filled with champagne, I can move around and I have enough degrees of freedom to balance everything. Now start running. You won't run a long time with your plateau. So your dimensionality decreases and the requirement from the brain to do and control the movement precisely increases as you increase your running speed. And that same happens with other movements and other tasks. So, in fact, as long as we are not demanding, we have the ability of multitasking, but otherwise not.
Vinzenz, what is a micro shear force?
Well, I had to find a good word for it.
Yeah, I know. I say it tongue in cheek, but
so we needed to define it, and I would say it goes into that thing where I think we should debate things. Mm-hmm. And if you look, for instance, at Walter's measurement with the charcoal paper in the joint and so on, and others, Walter would say, with these two muscles, you don't have too much medial lateral forces. They go over the patella, and so why should you have a medial lateral? And my argument is they come in two directions. If they don't have the same force or appropriate force, you will have a medial lateral, to be proven. But from a vector calculation, you must have, with two forces, a force that goes medial lateral. Now, we were always considered that the cartilage is compressed. And so all the hypothesis about cartilage damage and so on was mainly on the compression force on the cartilage. Now I said, what happens if these motor units are not synchronized? Then in fact, this force is now suddenly wiggling like this. So you get now a medial lateral force that is constantly present. That doesn't need to make it move. So it won't be a movement across, but it's like a wire that you would just bend a little bit on both sides. If you bend that 1,000,000 times, then it breaks. And so I wouldn't call that the shear force in the sense measurable big thing, but I would say it's just an unloading in one to the other direction and will be a minuscule, a very, very small force, but just changing the orientation. And that's what I call a micro shear force. And that is now the hypothesis. That's not proven. So the hypothesis is that, like if you have a wire that you shake like this causes inflammation, this causes damages. And if that is true, then the osteoarthritis patients should in fact show a smaller coherence. That is one of the projects we are following. If that's the case, we will have the biofeedback, and we can see whether we can recover that loss. And so that would be a complete alternative to the current view of what damages the cartilage.
And so by micro shear, we're not talking about a force on the order of millimeters. So we're not talking about very, very small.
I have never made, in fact, the actual calculation, because then you have to account for the friction, and you have to see how much, in fact, resistance would you have to have a change in direction without having a movement. So at some point you have to overcome the friction. Now the friction is very low, so these forces will be extremely low. So I think they are so low that they are in the range that they could be reflecting single motor unit actions.
What do you think influences the maximum level of organ synchronization? I saw that they got up to 60, 70, and it was very subject specific.
It's subject specific, but I think it's just the task you have to do. And the brain uses, and if you think from the entropy point of view, every organized system uses energy. So if you want to synchronize your motor units to the extent that you see in the Piper rhythm and that you see by fast runners, then you use energy for that. Now the body wants to save energy. So if you just hold a basket or you just hold a little thing, you won't see much of that. So really the body minimizes the energy that it's needed, and the energy is energy of organization.
And what about fiber type distribution? You have a very homogeneous muscle where, say, they're all slow twitch or all fast twitch. Do you think you can get a higher level of synchronization in that case versus a very mixed muscle?
Well, that are all open questions. I think we made in a paper where I, in fact, debated with Farina what we see in the different bands of our spectrum. We interpreted high frequencies and low frequencies as coming from different fiber types. I still think that approach is correct. But what we see now is that superimposed to that influence on the power spectrum, we have an influence from the clustering, which seems to be bigger. So I have to revise a little bit the views that we had at that early time of wavelet transform, and today say be careful, it could be not only fiber type changes, but it could be clustering changes. So that whole idea of clustering becomes extremely important in the interpretation and how to discriminate fiber type effects on the spectrum compared to clustering effects and fatigue effects.
Are there any final questions for Vinzenz? Thank you very much.